First of all, let me introduce myself. I'm Emir Karamehmehtoglu, and I work at Aarhus University. I'm a postdoc there working on observations of core collapse supernovae. And I've been using the NOT for several years now, including with Jesper previously and with Max as well, and as part of NUTS especially. And I've triggered many OBs. I've even done a class where I've observed remotely with it, but I've never had the chance to go up and observe myself, and I'm hopefully going to get to do that this week. So I'm pretty excited. I was actually looking forward to that. But anyway, let's give a little outline of my talk. Works. Try again. All right. Okay. So I'm just going to talk briefly about the observational needs that we were trying to that the NOT help solve, but because I have some different ideas than what maybe Jesper and Max presented and what this object captures. And part of that was a project now called POISE, but this data was taken under NUTS. And then I will go to my object, which was a supernova 2020lao. It was a 1C-Broad9 supernova. I was hoping to get an introduction to that previous talk, but I'll try to provide something real quickly myself. And I just want to say that this is going to be mainly an observational talk, so not much science in it right now, but if you have comments or you want to talk about the science, you can just come find me afterwards, preferably with a cerveza or something like that, or you can just ask. So the need that we have is rapid follow-up, which comes around because of surveys that have been now discovering supernova shortly after explosion. So we've heard about ZTF, there's Atlas and Assassin as well. So here I'm showing an example. We have a non-detection in ZTF, a public light curve, and then 2 hours later, actually exactly 2.2 hours later, 2 hours and 20 minutes later, there's a detection about one magnitude brighter. And we followed this object up as part of a test for what we were calling POISE during 2020, during COVID. And so we had to use a variety of telescopes, which thankfully did not also using service time. And the basic idea behind the proposal is that we need high precision, rapid cadence, multi-wavelength observations to really expand our knowledge of the origins of supernova, because these early phase observations have really key insights into both the environments of supernovae, the explosion physics, and even the what comes out, the parameters that you can get a handle with using the light curves. Now, ideally, this telescope should be located somewhere so that it can shadow the survey that you're doing. Although we heard about a different example before with the young supernova experiment where you're going before it. But if you want to follow up something that's discovered here, you have no guarantee from ZTF or any other survey that's currently proposed that you are definitely going to get these points, and you're not going to get spectra, you're not going to get multiband wavelength coverage, which you really need if you want to study this early time in detail. So POISE is this precision observations of supernova explosions, whatever. There's an ATEL about it. If you want, you can go look it up. But what we did was in 2020, we did a precursor, and we made extensive use of NUTS data. And what we found out, we learned some lessons from this that we applied to POISE. And something that we learned was actually that for the phases of the supernova that we're interested in, really what we want are star supernovae. So we want Hollywood rock stars that are really well observed, just under the flashlight all the time. And that's better for us than bad samples. And losing even one of these is problematic. So for that, of course, one observatory is often not enough. Having multiples really helpful, and you need access to general instruments at a telescope like the NOT, where you can be crucial for maintaining both spectroscopic and photometric coverage of your object. And you also need both TOO time, so for following these things very early, and less time-sensitive follow-up. All right. Skipping now, talking about supernova 2020 LAO. This was an object that was discovered seemingly within hours of explosion. I say seemingly because it turns out the public ZTF light curve was deceiving us, but I'll get to that at the end with a slide if I can. What we did was within about a day of explosion, we started getting spectra with the GTC, and then later, when we couldn't, we started getting spectra with the NOT, and we got multi-band wavelength. Okay, multi-band photometry about 2 days after first discovery. And it's what's really nice about this is that, first of all, you have from few hours after discovery, we start getting multi-band coverage, but also it turns out to be this type of supernova called a 1C broad line, and it was relatively nearby at around redshift 0.03, located outside of a nice spiral host galaxy at about 140 megaparsecs, so we knew that we'd be able to follow it up for a long time. There we go. I was hoping that this would be covered in the previous talk, but just a brief overview. What is a 1C broadline? Why was I so excited to find this object? Well, they're thought to be the explosions of really massive stars, and they're often not always, of course, but they're sometimes actually found coincident with GRBs, so gamma ray bursts that you discover, and then the supernova that comes afterwards is, of course, can be followed up shortly after explosion. However, for this object, we think we are doing it the other way around, right? We're finding the supernova, we don't see a GRB, and nevertheless, we're getting very early time data that doesn't have any GRB contamination. A 1C broad line, by the way, is so that these very massive stripped envelope star, as the enveloped hydrogen or helium layers are lost, you're going to be left with some sort of a star that has probably a CO core that's high mass, and when it explodes, it's relativistic in velocity, so you have these gigantic, very broad absorption features, and that's what a 1C broadline supernova is. So why is this object exciting? I said it now a few times, but I wanted to really drive it home. You have an explosion constraint of a few hours. We have high-quality spectra starting at day 1. There's no afterglow component that can be found, and turns out that it was also covered by TESS. TESS is this small satellite that takes pictures of the sky, technically like every second or something like that, but you get bin data downloaded to Earth every 15 to 30 minutes. I think here's 30 minutes. And so we have this amazing coverage, although very noisy. It's a tiny little microsat that begins before our observations. That allows us to really explore what this supernova was doing before. And we don't see any sort of optical afterglow here. We have pretty deep non-detection limits, both from ZTF, we have a few others, also from other telescopes surveys, including Atlas. And in the spectra, we don't really see evidence of any optical afterglow component. So I'm just going to present the data that we have obtained. And we, of course, got photometry. So this is a very busy figure. I'm sorry about that. So we have, let's go panel by panel. You have phase since discovery. So that just means rest frame days since discovery. In the x-axis and the y-axis, you have some sort of scaled magnitude. And we have, BV, GRI. Several of these data points, especially at later times, comes from the NOT. There's also the ZTF light curve blended in here. We have test data, like I talked to you about. It's really difficult to visualize this data because it's very noisy, and there are a lot of systematics associated with it. What's interesting, however, though, is that this object seems to be a otherwise relatively normal 1C broadline supernova in terms of the photometry. It's here on the right panel, it's the same magnitude versus phase figure, except now I'm comparing to, in this dark red and green, to stereotypical or prototypical Type 1c broadline supernova 98BW, and this one, the green one, is 06AJ, which we think looks like 2020 LAO. And what we found is that, of course, 20 LAO is not as bright as these supernovae which are associated with GRBs, but when you compare it to a sample of 1c broadline supernova, the light curve is relatively similar. These have been normalized to peak, but it's rapidly evolving. Also, we discovered that the color evolution, which might be a little bit behind the microphone for some of you, but we plotted 1C templates on top of the color, so the color evolution is very typical of a 1C supernova. However, there's some early flatness here, could be something there. And once again, we don't see any evidence for an afterglow. What really helped was the not lake time data, which helped confirm the colors and help us get follow-up observations, spectra. Okay, sometimes works. All right, so we have, like I said, we followed up extensively with optical spectroscopy, and after our first two observations, thanks to ALPHOSC, we were able to get optical coverage at +3 and +5 days, which was really nice because some of these other listed spectra didn't end up being so high quality. And we were able to really cover the early, but also the whole evolution, and that was really crucial for the early evolution, but as well as getting a spectrum around peak. And this is what that spectral evolution looks like. So once again, one of these dreaded multi-panel figures, but you have wavelength on the x-axis and some sort of flux, and as time goes on, you're going downwards. So at +0.9 days after discovery, we got the GTC spectrum where you clearly see supernova features. There doesn't seem to be any sort of contamination from an afterglow, and we have data all the way up to almost 100 days after explosion. And I want to point your attention to this comparison figure on the right here, where I take the same epochs, at the same time as we have in the left figure, but we compare in dark red to this supernova 2006 AJ, which is a well-known and well-studied 1C broadline supernova. And if you look at here, the part around 8,000 angstrom is the calcium, and is often a blended calcium and oxygen feature for 1C broadline supernova, although in 06 AJ, here's the oxygen, here's the calcium, so it's separated. For 20 LAO, there does seem to be some sort of oxygen feature there, but it's very hard to see if it's there or not. It's definitely not something super broad as you would see in these extreme GRB supernova. So we thought that's kind of interesting. Why is that happening? All right. From now very preliminary here. Selected model comparison. So just to bring your attention again to the figure up here, that's data, I think, +12 days. That might actually be the NOT spectrum, yeah. That was compared to 98BW in black, and you see that normally you have this giant blended feature where we don't have it. So we used spectral models that computed for a different 1C broadline supernova, and here I'm just scaling it and plotting it on top, so this is not any fit or anything like that, just to see whether we see the same features in 20 LAO as we see in these models, and we do. And you can see that this oxygen feature around here can be modeled based on how much oxygen you see. And anyway, what we find is that in general, we actually can model it pretty well, which is not shown here, but the small difference is that there's a difference in the opacity of oxygen at the very high velocity layers. Okay, I will skip forward from this, and let me talk about this. Let me talk about this issue where we were trying to constrain the explosion epoch. So it's been a year and a half now since the ZTF light curve has become public. That means the data actually also becomes public, and you can go download it, which you should if you're ever relying on the upper limits that you get from the So here is a clear non-detection taken a few days before our discovery. Here is the first detection. Clearly, the supernova is there. And what we did was we looked at the upper limit that I showed you. That was 2 hours before. And, well, I see a supernova there. So I see there's some sort of transient flux there. So thankfully we have test data to try to nail down what we see, and we also have atlas data. But in general, you should be wary if you're using something like this. So they say necessity is the mother of all invention. I don't know who said that, but apparently it comes from Plato or something like that. So I created this thing called ZTF PHOT. It's using, thankfully, the publicly available ZTF force photometry interface. You can get force photometry of these ZTF targets when they become public, and then you can reduce it yourself. And by dragging sliders around live, you can actually go to this website now if you want to. It's on a free hosting service currently, so it might be a little slow if more than 1 or 2 people try it. But you can plug in your force photometry that you get from ZTF, and you can vary the parameters, and live dynamically the final light curve will update. So you can try and not fall for what I did. So here is the same R-band image, and that one point there is what we thought was a non-detection, what I now know is a detection. Thankfully, with the TESS light curve, we know that we estimate that the non-detection could have been, well, what I'll say is, with that, we think it's not a 2-hour discovery, but it's more like a 6-hour to 8-hour discovery. So it's still pretty good. So we're still within the first few days after explosion, more than likely. And I'll just end here with a mention of flow. So the data that I reduce, I use this pipeline. We created this photometry pipeline called flows. It's based on a project that Luis will explain soon. The photometry pipeline is public on GitHub. You can try to go use it, although it is, this is just calculating the transient photometry. And of course, the spectra were reduced using AlphaSQI, which was provided by NUTS. And, so you have AlphaSQ in there or NutCam in there. And this is mostly, it's currently not set up to be able to be used freely without, hosting your own database, but all the code is in there. So if you have any questions about it, you can ask me. All right, so I'll get to the summary now. I went over time a bit. Basically, my summary is that NOT enables rapid transient science. You can find objects that are really interesting if you follow them up, and you both need TOO time so that you can get this early object, but you don't have to wait several days or a day even for the first spectrums saying that it's been classified as such and such type before you start to get your follow-up data. If you have the possibility to trigger it yourself, then you can really just follow these objects quickly. And we're doing that with POISE, but not part of this talk. And redundancy is really key for this, because when we ran this experiment, we obviously followed up many different supernovae, and what would happen, of course, is that if you lose even a little small section at the early times, then you're not then that one is basically not useful for you. So if you have a specific thing that you want to study, for example, the early light curves, you really want to be able to have redundancy and be able to access a telescope like the NOT as well as whatever else you're using. And yeah, finally, the supernova 2020lao is a 1C broadline supernova that doesn't seem to have any afterglow contamination, not associated with any GRB when we check. We looked at X-rays, we don't find any detections both before or after. So it's an exciting object that's enabled by the NOT. Thank you.